To study kinetics or rate of reaction, first we need to talk about a model known as collision theory. It has four properties. The first is particles must collide for a reaction to take place, but immediately you should realize not all collisions are leading to a reaction. So for example, if I put a hydrogen gas reacting with iodine, from now on you should realize this plus in chemistry is really bumping into each other or collision. So if the collision is successful, they are going to give you 2 molecules of hydrogen iodide. Now it's possible from 10 collisions, maybe one of them leads to a reaction. So first they need to collide. The next thing is they need to have enough energy to break the old bonds and form new bonds. And that minimum energy is known as activation energy, or E capital subscript A. And usually we show it in a graph of energy diagram, which x-axis is time or reaction coordinate and y-axis is energy. If this reaction is exothermic, reactants are up here, products are down here. And this is the minimum energy, usually a hump that you need to overcome before the reaction takes place. Now, a few notes that you should remember from past. The distance between reactant and product is known as enthalpy or delta H. Doesn't dictate your speed and never changes. It's set for a reaction. And the height from reactant to top of this curve is known as activation energy, the minimum energy you need. Now, the species that make it up here, they are known as activated complex. They do not have a real life, so sometimes they are referred to as transition state. They are highly energetic, which makes sense. They are at the top of the energy. So the particles need to have this minimum energy to be able to react. The last criteria for this model is they need to have proper spatial orientation, known as steric effect. So if we show hydrogen in a covalent bond, such as a tiny molecule like this, and iodine, if we make it bulkier. Now if they collide head on, this collision doesn't have proper sort of orientation. So they will bump here, but there is no reaction. No reaction. Why? Because their orientation is not proper. But if they bump into each other sideways, if your hydrogen is here and your iodine is here, then this is a perfect orientation. And yes, you will have a reaction and you will form hydrogen iodide plus another hydrogen iodide. So they need to have that geometry or steric effect in order to react. So 4 criteria. Now let's look at the rate in a little bit more detail. Rate is the speed at which products are formed or reactants are being consumed. So since this is being consumed, the reactant concentration goes down, it decreases, and the product is going to increase. Now, quantitatively, the rate is reported as concentration per unit time. It's mole divided by the unit volume, which is decimeter cube, divided by unit of time, usually seconds, minutes, hours, or days. Now, let's just look at one reaction, which we have nitrogen colliding with molecules of hydrogen to form ammonia. This is a very important reaction named after the person who made it efficient, Haber, Fritz Haber. We talk about him later. Now, what you should realize is nitrogen, as it's reacting, is being used up. So when we write the rate is minus a change in concentration of nitrogen. So the delta triangle indicates change over unit time. But also hydrogen is being consumed, and it's minus delta hydrogen over unit time. But what you should realize, the ratio is 1 to 3. So as one molecule of nitrogen goes, 3 molecules of hydrogen are going at the same rate. So what we can do is report them per coefficient, 1 over their coefficient. And now on the product side, we are producing ammonia, so we put plus a change in concentration of ammonia over unit time. But to compare it to nitrogen or hydrogen, it's 1 over 2. In reality, if we give it number, for example, if ammonia is being produced as 4 times 10 to minus 3 moles per dm cube per second, that means hydrogen should be 1.5 times as much. It should be 6 times 10 to minus 3 mole per decimeter cube per second. And if you're looking for nitrogen, it should be half as much as ammonia. If this is 2, this is 1. If it's 4, this one should be 2. So that's the proportionality of coefficients in terms of the speed at which one disappears the reactant and one shows up the product. If we give you a plot of change in concentration, a bracket to indicate concentration over time, the product ammonia is being produced, so it starts from 0. At beginning is very fast, then gradually it's slowing down because the reactants are being consumed. So one thing I just said, and you should remember, is the rate is not constant. At beginning fast, and gradually you go to gradient of 0 and you slow down. Now if we look at, for example, nitrogen is half as fast, so it's not as steep of a slope, but it's declining. You start somewhere, your initial concentration, and then you go down. And then you go to the point that you cannot react anymore. And this is nitrogen. And if we show you, for example, hydrogen, it's much faster. For every 1 molecule of nitrogen, you have 3 molecules of hydrogen being used up, and it has a steeper slope, and this is your hydrogen. So hydrogen is being consumed, nitrogen is being consumed. Ammonia, on the other hand, is being produced, and the rates can be compared to each other by just knowing the coefficients. So 1 over the coefficient is their proportionality.